Hello, everybody. Today's lesson is on defining the logarithm function and evaluating logarithms. And so you maybe have heard about logarithms and maybe got a little bit of exposure to logarithms in Algebra 1, but you probably didn't understand what a logarithm really is in terms of its mathematical definition. A logarithm is the inverse of an exponential function. And so we can start off by graphing a log function. If we have a function f of x equals 2 to the x, its inverse, since this is an exponential with base 2, you can tell it's an exponential because it has a variable as an exponent. So this is an exponential with base 2. So a logarithm with base 2 would look like this. G of x equals log base 2 of x. And so log is just an abbreviation for the word logarithm. And so we can graph our logarithm function, a log with base 2, by finding the inverse of this. And we know that inverses are always reflections across the line y equals x. And we can also get that by just switching the x and the y values. So for example, this point at 0, 2 would now be at 2, 0. Oh, sorry, that's at 0, 1 becomes 1, 0. And then this point at 1, 2 becomes 2, 1. And this point at up here at 2, 4 becomes 4, 2. And 3, 8 becomes 8, 3. And we can go the other direction. Negative 1, 0.5 becomes 0.5, negative 1. And negative 2, 0.25 becomes 0.25, negative 2, and so on. And so we see that this graph passing through these points would look like this, and they are indeed mirror images of each other across the line y equals x, which is the dotted line through the middle. So if you folded your paper on that dotted line, the red graph would land right on top of the black graph. Okay, so this is y equals 2 to the x, that's called an exponential. This is y equals log base 2 of x, that's called a logarithm. Okay, and so by looking at the relationship between the points and the y values for our log graph, so if we have x and log base 2 of x, let's just plot some of the points in the table so we can see what's going on, like 1, 0, 2, 1, 4, 2, 8, 3. What we want to recognize is the relationship between those values is the y value is the power that you raise 2 to get some number. So if we're trying to get 8, we have to raise 2 to the third power. If we're trying to get 4, we have to raise 2 to the second power. If we're trying to get 1, we have to raise 2 to the 0 power, and so on. Okay? So when we evaluate a logarithm, the answer to the logarithm is the exponent that you would raise the base to get an answer. So for example, log base 3 of 9. What power would you raise 3 to get 9? You'd raise 3 to the second power, since 3 to the second power equals 9. Okay? If we wanted to evaluate log base 3 of 81, we ask ourselves, what power should I raise this base to get 81? 3 times 3 is 9. 3 times 9 is 27. 3 times 27 is 81, so it took a fourth power to get there. So that is true since 3 to the fourth power gives us 81. So the answer to the logarithm, notice, the answer to the logarithm is the exponent. The answer to the logarithm is the exponent. Okay? So if we wanted to evaluate something like log base, let's do log base 5 of 1 over 25. Well, what power would we raise 5 to get 1 over 25? We would square it to get 25, and then we'd make it negative to put it in the bottom. So the answer is -2, and that is since the base raised to this exponent does give us 1 over 25. Okay, so that's how you evaluate basic logarithms. And what we can, on the next page, we can answer some questions based on the graph that we drew here. We can talk about the domain and range for f inverse using set notation. The domain, so if we smashed this graph onto the x-axis, we'd see that we only get the x-axis covered from 0 to infinity. There are no negative x values on this red graph. There are negative y values, but no negative x values. And so the domain is from 0 to infinity. The range looks like we have negative values going down forever and positive y values going up forever, so it includes positive and negative y values. It's going to be all real numbers, so from negative infinity to infinity. Intercepts, so this has a x-intercept at 1, 0. And it has an asymptote. This asymptote is vertical, and that's at x equals 0. Vertical asymptote x equals 0. Is the inverse function an increasing function or a decreasing function? So if you were driving along this curve going from left to right, it's climbing. It's getting taller and taller and taller as you drive along here, and so that's an increasing function. How does f inverse behave as x increases without bound? So that means when it says increases without bound, that means it's going to infinity. So as x goes to infinity, look at our graph. As x goes to the right, this graph keeps climbing up forever. So as x goes to infinity, y also approaches infinity. And then how about as x approaches 0? As x approaches 0, now it can only approach 0 from the positive side because there are no negative values over here. So x is approaching 0 from the positive side, so we put a plus after it. As x approaches 0 from the positive side, look at what's happening to the y values. As x gets close to 0, y is going to negative infinity. Okay, and based on the inverse relationship between f of x equals 2 to the x and f inverse, complete this statement. F inverse of 16 is log base 2 of 16. So what power would you raise 2 to get 16? To the 4th power. So wait, that's 16 is 4. So log base 2 of 16 equals 4 because f of 4 equals 16. Okay, so what I was doing when I was writing these examples out, these were the logarithm problems, but I was writing them in exponential form to show you why that is the answer to the logarithm. So these are in log form, and these are in exponential form. And so that's what this next thing at the bottom of 746 is talking about. If you have an expression like this, that's an exponential equation. We have a variable as an exponent. In logarithmic form, we have the same base. This is base b, and this is base b. And then log base b of a equals x. And so this is just like what I was writing up above. It's just that they did the exponential first and then the logarithm. And this will work as long as the base of our logarithm is always positive, and b cannot be 0. Also, a has to be positive. We can't put a negative number inside a logarithm. All right, so in this example, I'm going to go back and forth between the two forms. So this says 4 to the third power equals 64, so that means a log with the same base 4 of 64, the answer must be 3. The answer is always the exponent. So log base 4 of 64 equals 3 because 4 to the third power equals 64. Okay. Here we're given a log equation. Let's write it in exponential form. So that would be the base 5 raised to the exponent equals 1 over 25, and that is true. And this one would be log with the same base 2/3 of q is equal to p. The exponent is the answer to the logarithm. And then the last one is the base to the exponent equals the number inside. Okay, so I'd like you to go ahead and try, or actually, let's see. We can do this one together also. This one would be log base 3 of 243 is equal to 5. The base 4 to the exponent negative 3 equals 1 over 64. 3/4 is the base, so we have to put that here. 3/4. The answer to the logarithm is the exponent, so that's the answer to the logarithm is the exponent t. So the log of 3/4, log base 3/4 of s equals t. And the last one, 1/5 raised to the exponent equals v. Okay, so now pause your video and try number 8, converting from exponential form to log form or vice versa. Press play when you're ready to see if your solutions are right. So this is going to be log base 10 of 10,000 equals 4. The base to the exponent equals the number inside the log, 1/16. That is a true statement. This would be the log with the base 2/5 of b equals c. The answer to the logarithm is the exponent. And then again, the base raised to the answer is equal to the inside. So moving on to page 750, we can evaluate. This is our function log base 7 of x. So f of 243 means f of 343 means log base 7 of 343. So to evaluate that expression, we're asking ourselves, what power do I have to raise 7 to get 343? And so 7 times 7 is 49, and 7 times 49 is 343. So the answer to this is third power. We have to cube 7 to get 343. to find f of 1/49th. That's log base 7 of 1/49th. So again, we're asking ourselves, what power would I have to raise 7 to get 1/49? And the answer to that is -2. We would square 7 to get 49. And if we raise it to a negative power, then it goes down in the denominator and becomes 1/49. F of root 7. We can rewrite that as log base 7 of 7 to the 1/2. So what power do you raise 7 to get 7 to the 1/2? The answer is right there in front of us. It's 1/2. This base to this power equals that expression. 7 raised to the 1/2 equals 7 to the 1/2. So the answer is just 1/2. So we've looked at several different bases. We did some problems with base 7, base 2, base 10, base 3. One of the bases that two of the bases that we frequently use in math is base 10. So on your calculator, you have a log button right here, log. It doesn't say what the base is, and that's because that's called a common log, and it's base 10. So if I put in 100, for example, log base 10 of 100, it doesn't say base 10, but that's what that means. When you just write log with no base, that means it's a common log and it has base 10. So the answer to that should be 2, because 10 squared is equal to 2, and the answer is 2. If I did the common log of 100,000, that's 5, because 10 to the 5th power would be 1 with 5 zeros after it. So that's called a common log. So common log means base 10, and we just simply write it as log with no base. So no base means it's base 10. Okay, another base that we frequently use is that special number e, which is, remember, e is about 2.718. And since we use so many exponential functions with base e, it makes sense that we would also do a lot of logarithms with base e, and because that's how we're going to solve exponential equations that have an e in it, as we would use the inverse, which is the natural log. So the abbreviation for natural log, so that's log base e of x. We don't write it as log base e of x. We actually write it as ln of x. And the reason why it's ln, and it looks like this on your calculator, mine is right here, lowercase ln. The reason why it's ln and not nl for natural log, it seems like it should be nl, is because it's Latin, and any of you who have studied Spanish know that Latin-based languages put their adjectives after the noun, so they don't say white house, they say house white, Casablanca. So this is ln for Logarithmus naturalis. So natural log in English is, in Latin, would be Logarithmus naturalis, and that's why it's ln. Okay, so whenever you see ln, just think log base e. That might be easier for you. Okay, and so now you can evaluate either of those two types of logs on your calculator. So they just did examples here. Common log of 13. So common log of 13, they got 1.114 here. That's the same thing I got on my calculator by pressing the common log button and then typing 13. Okay, then the same thing for natural logs. To find the natural log of 13, we just type ln 13. Natural log 13 is 2.56. And the reason why is because e raised to that number is 13. 12.9 repeating is essentially 13. Okay. And so let's move on here. Okay, so on this 11 and 12, it says find the common log and the natural log. You use your calculator to find the common log and the natural log of each number. So go ahead and take out your calculator, find the common log and the natural log of 0.25, find the common log and the natural log of 4. So we want the log of 0.25, we want the natural log of 0.25. So here we want the common log of 4, and we want the natural log of 4. Okay, so go ahead and evaluate those on your calculator. Press play when you're ready to check your solutions. Okay, so the common log of 0.25 is negative 0.6. They said, let's see, what did they say to round to? They didn't. So we'll just put 602. And then the natural log of 0.25 is negative 1.386. It says verify by using the appropriate exponential expression. So for the first one, if we raise 10 to the negative 0.602, that's how we verify it. So 10 raised to the negative 0.602 should be an answer really close to 0.25, and it is. So this is about 0.25, which is the number we started with. For this one, if we do e raised to the negative 1.386, e raised to the negative 1.386, that's very close to 0.25 as well. So that confirms, since we got 0.25 for both of those, that confirms it. Okay, and then the next one, common log of 4 is 0.602. Natural log of 4 is 1.386. Notice they're the same answers but positive, and that's because 10 raised to the positive 0.602, 10 raised to the 0.602 is very, very close to 4, and e raised to the 1.386 is also very close to 4. All right, and then moving on to some real-life examples. Go ahead and read number 13, and then we'll work that one out together. Okay, so they actually give us the equation here, and all we have to do is fill in the pieces that we know. I is the intensity of the sound, and I naught is the intensity of the softest audible sound, which they said is about 10 to the negative 12th. So we know that I naught is approximately 10 to the negative 12th power. What is the intensity level of a rock concert if the sound has an intensity of 3.2? So we're saying I equals 3.2, and so the intensity level is 10 times the log of I over I naught. And so we just plug that into our calculator. 10 times the log of 3.2 divided by 10 to the negative 12. And the answer is about 125. So we'll say about 125 decibels. All right, and then number 14. Again, they give us the equation to use. This is the exponential decay equation. And we want to know when will there be 90 milligrams of beryllium remaining. So we want the left side to be 90. And we're trying to find out when does that happen. So that means we're solving for t. And so we can divide both sides by 500 to start with. And so that is 9/50 equals e to the negative 0.05 to the t. Now there's two ways to solve this from here. One is to rewrite this in log form. So if we rewrite it in log form, so I'll call this method 1. To rewrite it in log form, we would say the log with the same base of 9/50 is equal to the exponent, negative 0.05 t. Okay. Method 2 is to take the natural log of both sides. So I'll call this method 2, and we'll see that we get the same answer both ways. So method 2 is to actually take the logarithm of both sides. Okay, and so I'll solve method 1 first. So I just divide both sides by negative 0.05. Now this is a log base e, so that's really a natural log. And so to evaluate this expression, so those cancel, I get t equals, to evaluate the left side, I'm going to do the natural log of 9 divided by 50 divided by negative 0.05. And the answer is about 34.296. Okay. I'm using the other method when I took the natural log of both sides. I get natural log of 9/50 equals, now in this case we're doing a log base e, which is a natural log is log base e, so those cancel each other out. A log base e and an exponential with base e cancel each other out, so I just get negative 0.054, so those cancel each other out. We just get the exponent, and then let's see, there's a t there as well. That's not a 4, that's a t, so that's 0.05 t. And then divide both sides by negative 0.05 to get t by itself. And we get t equals natural log of 50 divided by negative 0.05, which is actually that same expression that's right there on my calculator, 34.296. So you can do it either way. When you're trying to solve for a variable that's an exponent, you can either change the equation to log form, or you can take the log of both sides. In this case, it was an exponential with base e, so that's why I took the natural log of both sides, because the natural log is the inverse of an exponential with base e. And so that's the logarithm that I took on both sides. Okay, in both cases, I got an answer of 34.296 seconds. Okay, and that's it for today's notes. Have a great day, everybody.